There are a series of properties of matrix arithmetic that we need to understand so that we could work on other forms of matrices and their operations as well. Now, this is just the first of the many. We have here the commutative law for matrix addition, which states that for matrix A and B, their sum is just equal to the sum when they are commuted, B plus A. Before we start, it's very important to understand that for this property to work, A plus B must be defined. Because if it's not defined, then we cannot work on this. And this video will allow us to show the truth value of this so that in our future dealings with matrices, this could be applied. When can we say that A plus B is defined? The sum of two matrices could only be defined if and only if they are of the same size. Say for example, if A is an m by n matrix, A plus B can only be defined if B is also an m by n matrix of the same size, not the other way around, or not with other sizes, because m here tells us the number of rows and n will be the number of columns. Now let's try to prove this by representing matrices A and B first in their general context, because this should all be true for all types of or all sizes of matrix as long as they are of the same size. So let us not assume a 2x2 or 2x3 matrix. Let's just say let A be equal to a matrix in this form. Of course, you have your component here, A11, A12, A13, until A to the number of row 1n. And for our columns, you have A21, A31, A of m1, the number of rows. So we have here A22, A23, A2n, A32, A33, A3n. And then as we go here, this would be AM2, this is a 3, right? M3, and this would be A of mn. Okay, sorry for that. And let's also assume B, and let's use B, our arbitrary values. You have B11, B12, B13, B1n, B21, B22, B23, B2n, B31, B32, B33, B3n, and of course you have here BM1, BM2, BM3, and you have here BM and n. So this might take a longer length of video because I need to show it in general form. Okay, so let's have it in this form here. Let's show that A plus B will reach B plus A later. So if you're going to have A plus B, of course, we're just going to add the representation of two matrices. You have A11, A12, A13, you have A1n, A21, A22, A23. You see that it would take a lot of time because we are assuming here this is true for all types of matrices, not just by 2x2, 2x3, or whatever sizes that would be. So please bear with me. A, M, N. Of course, this is plus, just like this one here. For B11, B12, B13, B1n, B21, B22, B23, B2n, B31, B32, B33, B3n, BM1, BM2, BM3, and BMN. Okay. Again, as mentioned, this only defined if you have the same size, because if they are of the different sizes, once we add matrices, we're going to add component wise. So if this is longer than that, then it's not possible, or if this is shorter than that, vice versa. So for the sum component wise, we'll have this form. A11 plus B11 for the first. Second, you have A12, B12. That's plus A13 plus B13 dot 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 to A1N plus B1, and this is A, sorry for that. Next, A21 plus B21, A22 plus B22, A23 plus B23, A2N plus B2N. You have A31 plus B31. Simply look at the components. A32 plus B32, A33 plus B33. You have A3N plus B3N. And of course, until AM1 plus BM1, AM2 plus BM2. Okay, pardon for this. AM3 plus BM3. This is dot 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 dot. You have AMN plus BMN. We have added all the components of our A and B. What is next now? We are talking about commutativity here, and these components here are now actually real numbers, where A to A, all of these components here are real numbers. And since commutativity already works on real numbers, we can compute them component wise. So let's commute them rather. If we are going to commute them, so pardon with this, I'm going to move here. Right. So we're going to commute. So we have B11 plus A11. We are commuting the components here. So this is B11. Same with the rest. You have B12 plus A12, B13 plus A13. You have B1N plus A1N, because we are now commuting them. Same with the rest. So we have B21 plus A21, B22 plus A22, B23 plus A23, B2N plus A2N, B31 plus A31, B32 plus A32, B33 plus A33, until B3N plus A3N. Pardon my handwriting. BM1 plus AM1, BM2 plus AM2, BM3 plus AM3, and you have here BMN plus AMN. Okay. So now that we have established commutativity on this, we can now break this into two matrices. And we can now break them into two matrices using all the first components of the sum as one components of the matrix. I'm talking about all, and the second components of each sum here would be for another. So basically, you will have an expression like this now. We are not taking all the first components of the sum: B11, B12, B13, B1N, B21, B22, B23, B2N, B31, B32, 32, B33, B3M, BM1, sorry, this should reach here, BM2, BM3, you have here BMN. These are all the first components of each sum. Then, since they're all under addition, plus the second components, A11, A12, A13, A1N, A21, A22, A23, A2N, A31, A32, A33, A3N, and you have here AM1, AM2, AM3, AMN. What is this now? Based on our representation earlier, with all the B components here, this is just equal to matrix B. And all the components of A here is equal to our components A. So basically, we can write this finally in this form. This is just your matrix B plus your matrix A. Now, we have shown that A plus B is just equal to B plus A as long as their sum is defined. This is about the commutative law for matrix addition. This is one of the videos for properties, laws, and theorems. Please subscribe now.